A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
You ever think about that split second after you hit the power button on your computer? But before the screen even flickers to life, there is this tiny, high-stakes drama happening in the silicon where your machine is essentially trying to remember how to be a computer. It is a moment of total vulnerability and absolute chaos, masked by a silent black screen.
It is the ultimate existential crisis for hardware, corn. You have these billions of transistors that are technically capable of performing trillions of calculations per second, but at the moment of ignition, they are effectively brain dead. They have no memory of what they are. They do not know what a hard drive is. They do not know how to talk to the system memory, and they certainly do not know how to load an operating system like Windows or Linux. They are just a collection of gates waiting for a signal.
Today's prompt from Daniel is about that exact moment of digital amnesia. Specifically, he wants us to look at the necessity of the BIOS and UEFI in modern computing. He is asking why, in 2026, we still have this black box living on a separate chip, and why we keep our firmware physically isolated from the high-speed storage where we keep our actual data. It seems like a bottleneck, right?
Herman Poppleberry here, and I have to say, Daniel really hit on one of my favorite architectural quirks. It feels almost archaic when you think about it. We have these lightning-fast NVMe Gen 6 drives that can move dozens of gigabytes per second. Yet we still rely on a tiny, relatively slow SPI flash chip to kick things off. But that separation is not just a legacy leftover from the 1980s. It is a fundamental security and architectural requirement. It is what we call the root of trust.
It is funny because most people only interact with the BIOS when something goes wrong, or if they are trying to overclock their system. We talked about that gatekeeping rule back in episode 684 when we were looking at voltage and frequency settings. But for the average user, the BIOS is just that blue or gray menu they accidentally trigger by mashing the escape or delete key. Why can't the CPU just be smart enough to look at the SSD and say, "Alright, there is the bootloader, let's go"?
Because it is a classic chicken and egg problem, corn. To read from an SSD, the CPU needs to communicate over the PCIe bus, but the PCIe bus has not been initialized yet. It does not have its clock signals, it does not have its power states defined, and the CPU does not even know which lanes are connected to what. To initialize the PCIe bus, the CPU needs instructions. Where do those instructions come from? If they were on the SSD, you would be in a permanent loop where you need the instructions to read the instructions. The system needs a known, immutable starting point that is hardwired into the silicon.
So the CPU is basically hard-coded to look at a very specific memory address the moment it gets the power good signal from the power supply?
In the x86 world, the processor starts in what we call real mode. This is a legacy 16-bit state that mimics the original Intel 8088 from over 40 years ago. It is a tiny, cramped little room of a processing state. The very first thing the CPU does is look at the reset vector. This is a specific location in memory, usually at address FFFFFFFFF. Through the magic of motherboard routing, that memory request is directed away from the main RAM, which is currently empty and useless, and toward that small SPI flash chip where the BIOS or UEFI lives. That chip is the only thing the CPU can talk to without needing a bunch of complex drivers.
It is like a survival kit for someone who just woke up with total amnesia in a dark room. You do not need to know how to drive a car or use a smartphone yet. You just need to know how to find the flashlight and the manual that tells you how to turn on the lights. But let's talk about the physical side of this. Why is this firmware on its own dedicated chip? We have plenty of room on our terabyte drives. Why keep this 16 or 32 megabyte file on a separate piece of hardware?
That is where the concept of the root of trust comes in. If your boot instructions lived on your main hard drive, they would be sitting in a user-writable area. Any piece of malware with administrative privileges could reach in, rewrite your boot sequence, and effectively own your machine before the antivirus software even has a chance to load. By putting the BIOS on a physically separate SPI flash chip, serial peripheral interface, you create a hardware-level barrier. This chip usually sits on its own low-speed bus, separate from the high-speed data lanes.
But wait, we can still update our BIOS from within Windows or via a USB stick. If I can write to it, can't a virus write to it?
In theory, yes, but the barrier is significantly higher. Writing to that SPI chip requires specific protocols and often hardware-level permissions. Many motherboards have a physical write protect pin or a specific sequence that must be triggered in the chipset. It is not like saving a Word document. You are communicating over a serial peripheral interface bus, which is totally separate from the NVMe protocol. This physical isolation means that even if your operating system is completely compromised, the foundation of the house remains intact. If the BIOS is secure, you can always wipe the drive and start over. If the BIOS is infected, the hardware itself is lying to you.
It is the difference between someone breaking into your house and someone rewriting the deed to the land the house is sitting on. If the firmware is compromised, you can't even trust the hardware anymore. I remember we touched on the physical layout of these chips in episode 637 when we were geeking out over motherboard design. It is usually that little 8-pin chip tucked away near the CMOS battery, right?
That is the one. And what is interesting is how the architecture has evolved. We moved from the legacy BIOS, which was very limited and could only address 1 megabyte of memory, to UEFI, the Unified Extensible Firmware Interface. The UEFI specification was officially handed over to the UEFI Forum in 2005 to replace the aging IBM PC BIOS standard. People often think UEFI is just a BIOS with a mouse-driven interface and better graphics, but it is actually a massive shift. It is essentially a tiny, self-contained operating system that runs before your actual operating system.
That sounds like a lot of complexity to add to a process that is supposed to be simple. If UEFI is a mini OS, doesn't that just create a larger attack surface? I mean, we are talking about millions of lines of code now, compared to the tiny assembly files of the 80s.
You have hit the nail on the head. That is the trade-off. UEFI brings a lot of benefits, like supporting drives larger than 2 terabytes and providing secure boot. Secure boot uses cryptographic signatures to ensure that only trusted code signed by the manufacturer or Microsoft, is allowed to run. But because it is so complex, it can have its own bugs. We have seen the rise of UEFI-level bootkits like Black Lotus or Cosmic Strand. These are incredibly difficult to detect because they operate underneath the operating system. They can intercept calls to the kernel and hide themselves before the OS even knows it exists.
This makes me think of the Intel Management Engine. That is another one of those black boxes that lives beneath the surface, right? It is basically a computer inside your computer that stays on even when the main system is off.
It is exactly that. The Management Engine, or ME, now often called the Converged Security and Management Engine, or CSME, is a separate microprocessor integrated into the chipset. It has its own operating system, usually a version of Minix, and it has full access to the system memory, the network, and the hardware. It operates at what we call ring -3. To give you context, your apps run at ring 3, your OS kernel at ring 0, and the hypervisor at ring -1. The ME is way down at the bottom. It is there for enterprise management, like remote wiping a lost laptop, but for a privacy-conscious user, it is the ultimate black box because you can't really see what it is doing or turn it off easily.
It feels like there are all these layers of ghosts in the machine before we even get to the desktop. You have the SPI flash chip with the UEFI, you have the management engine in the chipset, and then finally you get to the actual OS kernel. It is a very hierarchical structure. But if the goal is security through isolation, how does something like a Raspberry Pi handle it? They do not have a traditional BIOS chip, do they?
The Raspberry Pi is a great counterexample that highlights how different architectures approach the problem. On a Pi, the boot process is actually inverted. When you power it on, the main ARM processor is actually held in reset. It is the video core GPU that starts up first. The GPU executes a small bit of code in its own internal ROM. Then it looks at the SD card for a file called bootcode.bin. It loads that into its cache, initializes the SDRAM, and only then does it release the ARM CPU to start running the Linux kernel. It is much more dependent on the removable storage than an x86 PC. This makes it very flexible and easy to recover if you mess something up, but it does not have that same immutable foundation. Feel that a dedicated SPI chip provides on a motherboard.
So on a PC, the BIOS is the nanny that wakes up the CPU, but it is a nanny that lives in a separate, locked room. It seems like a lot of this architecture is about managing the sheer messiness of PC hardware. There are thousands of different motherboards, memory modules, and GPUs out there. The BIOS has to act as a translator, right?
That is its secondary role, which is hardware abstraction. The operating system does not want to know the specific electrical timings required to talk to the voltage regulator on your specific model of motherboard. The BIOS handles those low-level handshakes. It goes through several phases: SEC for security, PEI for pre-EFI initialization, and DXE, which is the driver execution environment. During these phases, it sets up the memory controller and performs what we call RAM training.
I love the idea of training the RAM. It sounds like the BIOS is putting the memory through a little boot camp every time you turn the computer on. What is it actually doing there?
It is literally testing the signal integrity. Because modern DDR5 or DDR6 memory runs at such high frequencies, the tiny physical differences in the length of the copper traces on the motherboard can cause signals to arrive at slightly different times. The BIOS sends patterns of data back and forth, adjusting the delays by picoseconds until the timing is perfect. If it can't find a stable timing, your computer won't boot. By the time Windows or Linux starts, the BIOS hands over a neat table of hardware information called the ACPI tables, Advanced Configuration and Power Interface. It says, here is a map of the house. I have turned on the lights and the heat, and I have identified all the occupants. Now you take over.
But what happens when that process fails? We have all seen those horror stories of a BIOS update going wrong and bricking a motherboard. Why is it so catastrophic compared to, say, a failed Windows update? If my Windows update fails, I just boot from a recovery USB. Why can't I do that with a BIOS?
Because if you corrupt that SPI flash chip, you have destroyed the map and the survival kit. The CPU wakes up, looks at that reset vector address, finds gibberish or zeros, and just stops. It does not know how to look at a USB drive because it hasn't loaded the code that tells it what a USB drive is. It is bricked because it has become as useful as a literal brick. This is why many high-end motherboards now include a dual BIOS system. They have two physical SPI chips. If the primary one fails, a hardware toggle or an automatic fallback kicks in and boots from the backup chip. Some even have a BIOS flashback button that allows a dedicated microcontroller to write a new BIOS file from a USB stick even if the CPU isn't running.
That feels like the ultimate in case of emergency break glass solution. It is interesting how much we rely on this tiny bit of silicon. It even handles things like microcode updates for the CPU, right? I remember when the Spectre and Meltdown vulnerabilities were a huge deal. The fix often required a BIOS update.
That is a perfect example of why this architecture is so vital. When Intel or AMD find a fundamental flaw in how their processors execute instructions, they can't exactly recall millions of physical chips. Instead, they write a microcode patch. But because the CPU is volatile, meaning it loses its state when it loses power, it loses that patch every time you turn it off. The BIOS acts as the delivery mechanism. Every time you boot up, the BIOS loads that microcode patch into the CPU's internal SRAM before the operating system even starts. It is a way to repair hardware using software, but it has to happen at that foundational level.
So the BIOS is essentially the gatekeeper for the very soul of the processor. It is fascinating that in 40 years of computing, we have moved from floppy disks to cloud storage, but we are still tethered to this tiny chip on the motherboard. Is there any move toward an open source version of this? I have heard people talk about coreboot.
Coreboot is the big one. It is an open source project that aims to replace the proprietary UEFI or BIOS with a minimal, transparent bootloader. The idea is to have a lightweight firmware that does the bare minimum to initialize the hardware and then hands off to a payload like Linux. It is very popular in the privacy and security community because you can actually audit the code. You do not have to wonder if there is a backdoor in your BIOS if you compiled the BIOS yourself.
But I imagine that is a nightmare to support, given how many different motherboards are out there.
It is a massive undertaking. Each motherboard needs specific blobs of code to handle things like the memory controller initialization, which manufacturers are often reluctant to share for competitive reasons. This is why you mostly see core boot on specific laptops like the ones from System 76 or older ThinkPads. It is a battle between the desire for an open, transparent root of trust and the reality of complex proprietary hardware.
It really highlights how the BIOS is the bridge between the physical world of electricity and the logical world of software. It is where the hard in hardware meets the soft in software. But let's get into some practical takeaways for the people listening. If this is such a critical part of our machines, how should we be treating it?
The first rule is, do not fix what is not broken. Unlike your graphics drivers or your browser, you should not update your BIOS just because a new version is out. You should only update it if you are experiencing stability issues, if there is a critical security patch, or if you are upgrading to a newer CPU that the old firmware does not support. Every time you flash that chip, you are performing open heart surgery on your computer. If the power goes out mid-flash, you are in trouble.
And if you're going to do it, make sure you are not doing it during a thunderstorm.
Use a UPS, an uninterruptible power supply, if you have one. Also, people should get familiar with the security settings in their UEFI. Things like secure boot are often misunderstood. While it can be a pain if you are trying to install a niche Linux distribution, for the vast majority of users, it is a vital layer of protection. It ensures that your bootloader hasn't been tampered with by a rootkit. It creates a chain of trust from the hardware all the way to the OS kernel.
What about verifying firmware integrity? Are there tools for that?
There are. Most modern operating systems have ways to check the status of the firmware. On Windows 11 or 12, you can use the device security menu to see if your core isolation and security processor features are active. This tells you if the OS is successfully communicating with the hardware-level security features provided by the BIOS and the TPM.
The TPM, the Trusted Platform Module, is another one of those separate chips, right? It is like the BIOS's sidekick for encryption.
It is. It stores cryptographic keys in a way that is physically isolated from the rest of the system. Between the SPI flash chip for the BIOS, the management engine in the chipset, and the TPM chip, your motherboard is actually a crowded neighborhood of small, specialized processors all working to keep the main CPU in check. It is a system of checks and balances.
It is a lot more crowded than I thought. I think what is really interesting here is the shift in perspective. We tend to think of our computers as these monolithic things, but they are actually these federations of independent components that have to negotiate with each other every time we hit the power button. The physical separation Daniel asked about is the only thing keeping that negotiation honest.
That is a great way to put it. If the storage was not physically separate, there would be no way to verify the state of the machine. You need a source of truth, that is, outside the reach of the software you are trying to run. It is the same reason why you do not keep the key to the safe inside the safe. You need a physical boundary.
Although, knowing you, Herman, you probably have a safe for your keys and a key for your safe.
I will neither confirm nor deny the existence of my nested safe architecture, but I will say that the more you learn about firmware, the more you realize that the black box is actually the most interesting part of the machine. It is where the laws of physics are translated into the laws of logic. It is the moment where electricity becomes information.
It is the foundation of the whole stack, and it is a foundation that we largely take for granted until it stops working. I think the takeaway for me is that this archaic seeming isolation is actually a very elegant solution to a very modern problem. We need that physical boundary because software is inherently fluid and vulnerable. Hardware is stubborn, and in the case of the BIOS, stubborn is exactly what you want.
Stubborn and predictable. That is the goal of the boot process. You want the exact same thing to happen every single time you hit that button. You want to know that the code running at address 0 is the code you put there, not something that crawled in through a web browser 3 weeks ago.
So, looking ahead, do you think we will ever see a world where the BIOS disappears? Where the CPU is just inherently aware of its surroundings?
I think we might see the physical chip disappear, but not the function. We are seeing more integration, where the firmware is being moved into the CPU package itself, especially in systems, on a chip like you find in smartphones or Apple Silicon. But even there, they use a mask ROM. This is a tiny bit of memory that is literally etched into the silicon at the factory and cannot be changed. The physical separation might shrink to the microscopic level, but the architectural separation will always have to exist. You will always need that first instruction that cannot be lied to.
The immutable word. It is almost poetic when you get down to it. The CPU wakes up in the dark, reaches out, and finds that one familiar handhold to pull itself up.
And then it spends the rest of its time trying to run as fast as possible away from that moment. But it always has to go back to the beginning eventually. Every reboot is a rebirth.
Well, I think we have thoroughly explored the basement of the computer architecture today. It has definitely made me appreciate that black box a little bit more. It is not just a menu, it is the anchor for the entire system. Without it, we just have a very expensive space heater.
It really is. And it is a great reminder that in tech, sometimes the oldest ideas are the ones that are the most indispensable. We keep building higher and higher, but the foundation stays pretty much the same. The BIOS is the silent guardian.
I think that is a good place to wrap this one up. We have covered the chicken and the egg, the survival kit, and the nanny in the locked room. This has been a deep dive into the silent guardian of the boot process.
Thanks to our producer, Hilbert Flumingtop, for keeping the show running as smoothly as a well-trained RAM module.
And a big thanks to Modal for providing the GPU credits that power the show and keep our own virtual neurons firing.
This has been my Weird Prompts. If you found this dive into the BIOS interesting, a quick review on your podcast app helps us reach more people who like geeking out over silicon.
We will be back next time with whatever weirdness Daniel sends our way. See ya.
See ya.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from sloth.